Thanks. Begin with a word prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. And we thank you that you loved us so much that you came to earth to die for our sins. If we're just willing to accept you into our heart, Lord, we thank you for being a good and gracious God that you are, Lord. In your name I pray. Amen. Okay, so are there any questions before I get started? Or? Not yet. Okay. Laplace transforms. So that's what we'll talk about today, is the technique of Laplace transforms. And basically, this is yet another way to do many of the problems we already know. And it's also a nice way to do some of the problems we could do, but it would be really tedious. Especially, so like we have problems that have a discontinuous forcing function. You know, if you have a force which has like, it's case-wise defined in 3 different cases, the way we would solve that before would be, we'd solve the first case, and then we use continuity to match the first case to the second case, and then we'd use continuity to match the second case to the third case. So it's like solving 3 separate problems and like gluing the C1s and C2s together to make it work. I mean, it's real quite a pain. We did this for one example earlier in the course. Well, Laplace transforms have this way of smoothing together discontinuous cases into one big sweeping calculation. So that's one of the major motivations for talking about the Laplace transform. But it'll be a while before we get to that. So let's just give me. Here's the definition. The Laplace transform of y is going to be the integral from 0 to infinity of e to the minus st y of t dt. Now sometimes the notation here is that this is big Y of s. All right. So sometimes people will say that t is the time domain. You know, it's in the time domain, whereas s is the so-called frequency domain. I don't really intend to explain that. I'm just saying that's language people typically use. Let's work an example. So this is example 2. We worked out the Laplace transform of 1 last time. We figured out it was 1 over s. So I'm going to do an example which supersedes that example. Here we go. So e to the, let's say, at. All right, so what's the Laplace transform of the exponential? We have the integral from 0 to infinity, e to the minus st, e to the at dt. All right, so what's that do? Well, that's the integral from 0 to infinity. Properties of exponential, that's e to the minus parentheses s minus a times t dt. So I use the laws of exponentials and factored out a minus. Now you can integrate this thing. So this is minus 1 over s minus a, e to the minus parentheses s minus a t, evaluated from 0 to infinity. Now, if s is greater than a, then the infinite term drops out, because then s minus a is positive, consequently minus parentheses s minus a is negative, e to the minus infinity 0. So only in the context that s is greater than a does this integral converge, right? But for s greater than a, we're just going to get 1 over s minus a for s greater than a, right? So that comes from plugging in 0, you get minus the minus because of FTC part 2, right? So there you have it. There's a Laplace transform. The Laplace transform of an exponential is 1 over s minus a. Specific subcase, right? If you put a equals to 0, what do we get? E to the at is just equal to e to the 0, which is 1. And we recovered the example we did last time. The Laplace transform of 1 is simply 1 over s. Okay? Yep.
What's the s exactly?
S is the transformed variable. So we're trading functions of t for functions of s.
And what's the motivation for solving Laplace transforms just as a whole?
It gives us, because it allows us to solve discontinuous problems in a nice way, is my best answer. There is a motivation in terms of an analog to, there's some analogy to something else that you might have seen before. If you look at my notes, I have a link to a lecture by an MIT professor where he spends about 30 minutes trying to motivate it. You might find that to be motivating, so you can look at that if you want, but well, you can look at your book, see what the motivation of the Laplace transform is in your book. I wouldn't look. It's not there. Okay, so, because it's, well, anyway. Okay, so, still makes sense. If A is equal to alpha plus I beta. Also, you can prove that the Laplace transform of, let's say y1 plus y2 is equal to the Laplace transform of y1 plus I times the Laplace transform of y2. So, I mean, you can also do other things, like you could, more generally, you have additivity. I mean, certainly, you can easily convince yourself the Laplace transform of f plus g is equal to the Laplace transform of f plus the Laplace transform of g, and the Laplace transform of a constant times f is equal to a constant times the Laplace transform of f. So, in short, L is a linear operator on functions. Now, what kind of functions? Well, you could look at functions from a real variable to the complexes, but we do need a particular criteria on the functions. The functions have to be such that the Laplace transform converges, all right? So I'll just make a, well, let me get back into that in a little bit. Let's not worry about convergence too much just yet. I want to continue with this calculation, otherwise I'm going to lose track of it, okay? We'll get back to the theory in just a second here. So just trust me, if you will. This calculation still is legitimate when A is complex, all right? And so what happens, on the one hand, you've got the Laplace transform of e to the alpha plus I beta. What is alpha plus I beta? So that's the Laplace transform of e to the alpha t cosine beta t plus I e to the alpha t, right? Sine beta t. And so I'm saying that that is equal to the Laplace transform of e to the alpha t cosine beta t plus I times the Laplace transform of e to the alpha t sine beta t. All right? 1. But 2, we also know that the Laplace transform of e to the alpha plus I beta t, right, is equal to what? Well, and I'm being sloppy here, right? What should I mean, I'm missing some things here. I guess it matters a little bit here, so I'll include it. Sometimes I get sloppy and forget to write the of s. Sorry about that. There's a point where it really does matter, so I should get in the habit of doing it. That's evaluation at s, okay? Okay, so this is what? This is 1 over s minus a, right? But here a is minus alpha minus I beta. All right? And so if I multiply that by the complex conjugate of the denominator, what's that going to look like? Multiply this by 1 in a sneaky way, so like s minus alpha, right, plus I beta. That's the complex conjugate, right? And I know from our previous work with complex numbers that if I multiply by the complex conjugate upstairs and downstairs, that will force this expression in s to be put into its Cartesian form, right? Real part plus I times imaginary part. So let's see here. That is going to give me s minus alpha over s minus alpha squared plus beta squared plus I times s minus alpha over s minus alpha squared plus beta squared. All right? So there you have it, the real part and the imaginary part, all right? And you can compare. So the real part of 1 has to be equal to the real part of 2, which gives me the Laplace transform of the cosine times an exponential is this term, right? And we also get that the Laplace transform of an exponential times sine is this term right here. So there you go. We've got 2 more Laplace transforms. The Laplace transform of e to the alpha t cosine beta t of s is equal to s minus alpha over s minus alpha quantity squared plus beta squared. And the Laplace transform of e to the alpha t sine beta t of s is equal to, what did I just say? Oh, I did something wrong there. Beta. Fun. You see what I did? When you multiply this out, what's the coefficient of I? It's I divided by the denominator. The denominator is real. It's s minus alpha squared plus beta squared. The cross terms cancel. That's the whole point of multiplying by the conjugate. But upstairs, I get 1 times I times beta. This is not s minus alpha here, right? What should be here? Just beta, yeah. There you go. So now we now possess 3 Laplace transforms, right? All right. Did I put it on here? Yeah. So let me give you guys a sheet. You get to keep this, and you can add notes to it and bring it to the next test. You won't get a card, you get this sheet, okay? Make sure you bring it. Otherwise, well, you know, it'll be harder. So here basically is, here's your life, the next couple of lectures. It's pretty much everything we learned. So our goal is to internalize the knowledge on this sheet and learn how to use it to solve problems. At the moment, we're in table 7.1. We have, we've shown 1, 2, and then also the last formulas. You notice that sine and cosine are special subcases of this, right? I mean, if I have this, I can easily get the sine and cosine from this, right? Alpha equals to 0. Alpha equals to 0, what's it give me? Yeah, s over s squared plus beta squared, and the Laplace transform of sine beta t beta over s squared plus beta squared. Yeah. All right, so definition is, see, I don't know if I might have to look this up so I don't do it wrong, but we can say a function has exponential order alpha, all right, if it meets a certain criteria. What is that? Oh, let me steal your book for a second so I don't butcher this. Thanks. Definition. What is exponential order alpha? Don't let me down, index. Let's see here. Exponential order alpha, page 357. By the way, next semester I'm changing to the 4th edition. Too much has been cut out of the 6th edition. We're missing that whole chapter on energy analysis. I'm very, very bitter about this. So, anyway, definition. A function, f of t, is said to be exponential order alpha if there exist positive constants, t and m, greater than 0, all right, such that the absolute value of f of t is less than or equal to m times e to the alpha t for all t greater than big T. I really don't have much to say about exponential order alpha, except to tell you that this is the criteria, or at least one criteria, that if you meet, the Laplace transform of such a function will exist. So basically this will imply that the Laplace transform of f of s exists, if I recall correctly, for s greater than alpha. Well, I don't even remember that, but it exists for some f's, let's say. A little bit rusty on that for some s. Maybe for s greater than alpha. I'm trying to remember. Yeah, I think it's for s greater than alpha. I should probably put a little around that. But so for example, you can show that cosine and sine have exponential order alpha equal to 0. And that reflects the fact that these formulas, these are good for s greater than 0. In contrast, the e to the at, right? That was only good for s greater than a. And e to the at, I believe, has exponential order a. Kind of like, okay, so e to the at has exponential order a. E to the at, right? I think that makes sense. You choose m equal to 1 and alpha equal to a, right? For example, f of t equals to e to the at, right? Just think about it. You can choose m equal to 1 and alpha equals to a, right? You could choose big T equal to 0 too, for what it's worth, right? It's pretty clear that that will satisfy the needed criteria, right? So for example, an exponential has an exponential order alpha. And that also, we proved that the Laplace transform of e to the at was what? 1 over s minus a for s greater than a, so that does seem to suggest that result is the correct one. Okay, so there's some of your basic ingredients. Let's continue to build the, yeah.
Mr. Ask, is this related to the concept of an order, the order of a function that we got like that? How long it takes an algorithm?
Oh, I have no idea about the relation to algorithmics. As far as I'm concerned, it's just a criteria to make this integral converge. And you'll see it used in certain theorems as we prove them. But not everyone, for example. Well, the proofs I do in here are a little bit sloppy, and I hope you can forgive me for that, but it's for a good cause. So here's a theorem. This is called the shift theorem. It says that the Laplace transform of e to the at times f of t of s, all right, is equal to the Laplace transform of f of t at s minus a. Or, in the other notation, if the Laplace transform of f of t of s is equal to big F of s, this is our usual notation, big F for the transform function, little f for the time function, then in this lingo, we have the following. The Laplace transform of e to the at times f of t of s is just equal to big F of s minus a. That's another way you can write this, okay? So-called shift theorem. Okay, so here's the proof. Integral from 0 to infinity of, well, sorry, what am I doing? So the Laplace transform of e to the at f of t of s is what? Well, that's the integral from 0 to infinity. E to the minus st by definition, right? E to the at f of s. So then, use the law of exponentials. That's e to the what? Minus parentheses s minus a t f of t dt. Nothing much going on here so far. Now what you do is make a substitution, right? So let's see here. How's it go? Curses. Oh, no, I'm an idiot. That's the thing, is there are other proofs. This one will sneak up on you. There are other proofs which actually require further calculation. Actually, this one we're done. Oh, look, a napkin. How convenient. Let nothing. Let us think. Let my people think. What is this? We've got an exponential minus some argument times time integrated against a function from 0 to infinity. That is, by definition, the Laplace transform. Not at s. See, s has been replaced by s minus a. So this is exactly the Laplace transform of, f of t at s minus a. That's it. It's so simple, it's shocking, really. Look at that. But you can already see this theorem at work over here in the results we've derived, right? So check it out. The Laplace transform of cosine is s over s squared plus beta squared, right? When we multiply that by e to the alpha t, what happens? S gets replaced with s minus alpha. See? It's just that. So, and likewise here to here. These are two examples of the shift theorem at work. Okay? So shift theorem is important. Sometimes. Probably a more important theorem is the theorem which involves derivatives. So here we go. If f of t is exponential order alpha as appropriate, and suppose f of 0 is given. I'm sorry, I'm saying too much jibber jabber. Let me just get to the point here. Words are very unnecessary. They can only do harm. Let's see here. So the Laplace transform of dy dt, all right, guys, is equal to s times the Laplace transform of y at s minus y of 0. Okay. Or, in other words, the Laplace transform of y prime is equal to s times big Y minus y of 0 in the other notation. Okay, so here's proof. Integrate from 0 to infinity d e to the minus st. I'm sorry, I keep forgetting to write the what I'm doing. I think I can get rid of this a little bit here. Give myself a little more room. so proof. Give myself a little more room to work. So the Laplace transform of the derivative. So this is the integral from 0 to infinity of e to the minus st times dy dt dt. All right? Now what you got to do is a little calculus. Very simple. But notice that the derivative with respect to time of e to the minus st times y, what's that equal to? Well, that's equal to minus s e to the minus st times y plus e to the minus st times dy dt by the what? Yeah, the product rule and the chain rule also. So if you look at what we have, right? Look at what we have. What we already have here is e to the minus st times dy dt, right? Those terms appear here. So I can trade those, right? I can trade those for the integral from 0 to infinity of the total derivative of the product of e to the minus st times y plus what? Well, plus s e to the minus st times y integrated against time. Right? I'm just using the product rule. So then what? This is e to the minus st times y evaluated from 0 to infinity. Right? Then I have plus s times the integral from 0 to infinity of e to the minus st times y dt. This is where the exponential alpha, order alpha thing comes in. If you want me to flesh out the details, the argument, why is it that the upper bound has to go to 0? Well, it's because y is a Laplace transformable function. It must be that the upper bound, when you calculate that limit, it goes to 0. What that leaves us with then is this thing evaluated at 0 with a minus, right? Which is otherwise known as minus e to the 0, right? Yeah, e to the 0 times y of 0, right? And then over here, what is this? Again, we need to just do some soul searching and remember what's the definition of the Laplace transform. Exponential times y, right? So what are you looking at here? The exponential times y integrated from 0 to infinity. That's exactly, right here, the Laplace transform of y. And so what we got? We've got s times the Laplace transform of y at s minus y of 0, which is exactly, or if you like, s times big Y minus y of 0. And that's the theorem. Es bueno. By the way, this is in your table 7.2. We have just proved the fourth item using y instead of f, right? Okay? Now, so what happens, folks, if we try to do this for the second derivative? Can you guys see? Let's try to calculate the Laplace transform of the second derivative. Continuing. How about the, and it's not part of the theorem, but this is just a continuing discussion. The Laplace transform of y prime prime of s would be what? This is equal to the Laplace transform of the derivative, right? That's what prime prime means. The derivative of the derivative, right? So we can apply the theorem to the derivative, and what's that give us? That gives us s times the Laplace transform of the derivative minus y prime at 0, right? I'm applying the theorem to y prime. Next, I apply the theorem one more time. So that's s times what? Times s big Y minus y of 0 minus y prime of 0. And there you go. S squared big Y minus s times y of 0 minus y prime of 0. And there you have it. This is the Laplace transform, right, of the second derivative. This is a very interesting, these formulas are fascinating, really, because what are they saying? They're saying that somehow this Laplace transform, it somehow incorporates in the transform the initial conditions, right? So rolled into the transform is the data of the the differentiation, but also the initial condition. It's all there, right? This is really interesting because it means that somehow the Laplace transform technique is automatically incorporating initial conditions, right? Can you guys tell me what the third one is without me actually doing it? In fact, let me just jump to the nth one. What's the Laplace transform of the nth derivative? It's going to be s to the power n y, right? Minus s to the n minus 1 y of 0. Minus s to the n minus 2 y prime of 0. And then minus all the way until we get to y to the n minus 1 of 0. Yeah. By the same pattern, just extrapolating from what we've already done. Hey, check it out. We now own equations 4, 5, and 6 in table 7.2, right? All right. Now, there's another important theorem that we have not taken ownership yet. That's the last equation in theorem 7.2. Like if you have t times a function, that gives you, the Laplace transform of the derivative of the function. Let's see here, maybe I should do that one next. Actually, I think what I'm going to do instead, there's a little bit more. There's certainly more in the realm of Laplace transforms for us to do, right? But I'm going to change gears here a little bit and show you how we actually solve a problem with Laplace transforms. Then we'll get back to adding to our list of transforms, okay? Because I know you guys are like, well, this is great, but maybe it's not great. But why, right? Why? So let me show you the why. Let me show you the why. Actually, while I'm waiting for that to dry, I'll just write, here's another theorem we can prove. And I'll prove it if I have time. But the Laplace transform of t to the n times y is what? It's equal to minus 1 to the n, the nth derivative with respect to s, the Laplace transform of y. So that's another thing we can prove. If you multiplication by t amounts to differentiation by s padded with a minus sign. For example, for an example here, let's see here. How about like, what would the Laplace transform of t be? That would be the Laplace transform of t to the 1 times 1, right? So allegedly that would be minus 1 to the 1 times the first derivative with respect to s of the Laplace transform of 1, which is what? Minus dds of, what is the Laplace transform of 1? Last time we proved it was 1 over s, right? So the Laplace transform of t, this is t, not t prime, is t to the 1, is 1 over s squared. So there's the Laplace transform of t. And you can figure out, like, what's the Laplace transform of t times e to the t with this just the same, right? Let's see here. What's the Laplace transform of, let me do that. I'm waiting for the board to dry over there. Sorry, guys. Sad but true. I had to wash my silly shirt, and it's still very wet. So here, while we're at it, while we're waiting for the board to dry, what's the Laplace transform of t e to the at? So it's going to be minus dds times the Laplace transform of e to the at. So that's minus dds of, what's that? Well, that's 1 over s minus a, right? Prove that first thing today. Differentiate that, what you got? Well, duh, I didn't need to do that. We could have shift theorem that, right? If we know this, shift theorem automatically says that, right? Right? Sorry, guys, I'm not being lazy enough. Okay. Now, obviously, I still owe you proof of the theorem about multiplication by t amounting to differentiation by s, right? I haven't, but the proof is very much like the ones I've gone over so far. So let me go to an example now. Let's solve y prime prime plus, let's say, gee, I don't know, y equal to e to the 3t with y of 0 equal to 1 and y prime of 0 equal to 2. Okay, so here's the technique. You take the differential equation and you calculate the Laplace transform of it. That's our first move. So the Laplace transform of y prime prime plus y will equal to the Laplace transform of e to the 3t. So this gives me s squared times big Y minus, let's see here, y, how's it go? S times y of 0. Y of 0 is 1, so minus s. And then minus y prime of 0, which is 2, so minus 2. And then plus big Y again. Is equal to, the Laplace transform of e to the 3t is what? 1 over s minus 3, am I right? Okay. So this gives me s squared plus 1 times big Y is equal to s plus 2 plus 1 over s minus 3. So you take the Laplace transform of the equation. Then you do algebra to solve for the transformed y, to solve for the big Y. We're almost there. How do you solve for the big Y? Just divide by s squared plus 1. So big Y will be equal to s plus 2 over s squared plus 1 plus 1 over s minus 3 times s squared plus 1. Okay. So we did algebra to solve the differential equation in the frequency domain, which is pretty awesome, right? I mean, this is all we got to do now is just work our way back to the time domain. There's the rub. So what I'm going to have to do is partial fractions on this piece. Part fractions. So what I have is I got 1 over s minus 3 times s squared plus 1. Partial fractions decomposition for that will be a over s minus 3 plus bs plus c over s squared plus 1. Multiply this by the denominator. And let's see here. So some easy picking. If I put s equals to 3, I get 1 is equal to 10a, right? So a is 1/10. Another low-lying fruit, if I put s equal to 0, that's kind of nice. 1 is equal to, let's see here, I put s equal to 0. So 1/10 is a, right? And s equal to 0 plus what? Over here I've got c, right? Times minus 3. Hey, I can get c then. So that says c is what? Minus 3 times c equals to 9/10. So c is equal to what? Minus 3/10, I think. So I've got A, I've got C, and I got to figure out B is, right? So there's any number of things you can do to figure that out. What do you guys want to do? Any suggestions for me? I don't know. How about let's just any old value. How about s equals to 1 is kind of nice, right? If I plug in s equal to 1, that gives me 1 is equal to 2a, which is 2/10, right? Plus b plus c, which is minus 3/10, right? Times s minus 3, which is what? Minus 2, right? So this gives me 8/10 divided by minus 2 is equal to b minus 3/10, which says that b is equal to 3/10 minus 4/10, yeah? Also known as minus 1/10. All right, fine. So it took us a little bit of algebra, but anything worth doing requires effort. Let's see here. So there it is, s plus 2, s squared plus 1 in partial fractions has revealed to me the dark secret, which is that this is 1/10. I'll factor out the 10th. And you got yourself an a, which is 1 over s minus 3. You got yourself a minus s over s squared plus 1. And what else? What else? Where were we? Oh yeah, the c, minus 3 over s squared plus 1. 3s over s squared plus 1. Now, of course, you can ask the question, why did you do this partial fractions, right? I mean, that's an obvious question you should ask. It's like, that's great. Why on earth did you do that? There's a very simple reason I did that. How do you solve a differential equation here? You take the Laplace transform, right? Solving the differential equation involves undoing the Laplace transform. So this is called the inverse Laplace transform. So basically, here's the definition. This is the Laplace transform. So definition, L inverse of y of s is a function of t. And by the way, it's just y of t. So there's the inverse Laplace transform is just the other way. Now, this sheet you have, right? If you look at the sheet, the table of Laplace transforms, right? If you go from left to right, that's Laplace transform. But if you go from right to left, that's the inverse Laplace transform. In order to do the inverse Laplace transform, you actually have to have things that are in the table, right? If I ask you, what's the inverse Laplace transform of 1 over s minus 3 times s squared plus 1, and you look at the table, it ain't there. By the way, the inverse Laplace transform is also linear. So we can pull out constants. So getting to the story, long story short, we take the inverse Laplace transform, and that gives us y of t is equal to, okay, what's the inverse Laplace transform of s over s squared plus 1? It is cosine t. What's the inverse Laplace transform of 2 over s squared plus 1? That's plus 2 sine t. Then you've got plus 1/10. This guy, this guy right here gives me e to the 3t, right? This one gives me minus, what do we got here? Cosine t. And this gives me minus 3 sine t. And there you have it. Now we can check our answer. If you plug in 0, yeah.
I think I missed something. Where did that come from?
That's the inverse Laplace transform. If the Laplace transform of cosine is s over s squared plus 1, the inverse Laplace transform of s over s squared plus 1 is cosine.
Okay. But we know that's the solution to the differential equation.
Because we started with the differential, y was a solution to the differential equation at the outset, little y. Yeah. This is the technique. Yeah.
So pretty much Laplace just like glues everything together for us and makes it one calculation. And just
Yeah, I don't.
convert everything back to the original.
Right, and I don't think we quite appreciate that yet. You won't really fully appreciate that until I introduce the discontinuous stuff, which I'm not to yet.
Okay.
At the moment, all you see is that we didn't have to fit initial conditions. They just kind of get woven into the solution by the algebra. Now, you can ask the question, was it easier to do this the old way? Yeah, I think this is easier to do the old way. Like, I think the partial fractions calculation is more onerous than fitting constants to fit the initial conditions. But either way, this is a somewhat yucky problem. If we plug in 0, we get 1, right? And now I'm kind of worried. 1. And what happens here? 1 minus 1, which is what? 0, right? This is 0. So y of 0 is 1, like we want. Y prime of 0 requires a little bit more thinking. Y prime of 0 changes this to a minus sign, changes this to a cosine, right? Over here we get 3 exponentials. This changes to sine, that changes to 3 cosine. So you get, again, 3 minus 3 when you plug in times 0. And this just gives you the 2 cosine of 0. But, yeah, there it is. Of course, you can rewrite this and group the cosines together to make a nice, pretty solution. But where was I? Where, how do the initial conditions get wrapped into it? How does that happen? Where? See, it's right here. See, this is minus s times y prime of 0. It's going to be s times y of 0 rather, minus y prime of 0. These two terms. That's where the data got intertwingled, if you will.
So then you can still solve it if you weren't given initial conditions. You'd just be lucky.
Yeah, you can do the method of Laplace transform without initial conditions, but then, well, yes. Then you have to think about cases. Okay, so I'm going to have to, part of me, I really want to just dive into the discontinuous stuff and show you like what's interesting. But pragmatically speaking, what I should do for you is solve more inverse Laplace transform problems and so forth, so you build up your skill set, right? You have to be patient with me that we will do the interesting part eventually, just not today. Okay, so, and I tell you what, I'll skip the proof of this because it's not that interesting, and it's very much like the ones we've already done. So I'll spare you that. Another example. Let's calculate the inverse Laplace transform of something. How about s plus 3 over s squared plus 4s plus, let's say, 10. How would we do this? Okay, so what we've got to do is basically complete the square, right? Notice that s plus 3 over s squared plus 4s plus 10 is really what? It's really s plus 3 over s plus 2 quantity squared, right? Plus what? So I've added 4 by completing the square, right? So to be fair, my 10 has to become a 6, yeah. And then you got to use your imagination a little bit. And so I will use my imagination. S plus 2 over s plus 2 squared plus 6. Now, the reason I do that, I always have the table in mind. That will inverse Laplace transform to e to the minus 2t times cosine root 6. Then this one, what I'm about to do, requires a little bit more imagination. But here it is. This is obviously 3 over the square root of 6. Can't you see it? And then square root of 6 times s plus 2 quantity squared plus 6. The reason I do that is because now I can read, without further calculation, the inverse of the Laplace transform of s plus 3 over s squared plus 4s plus 10, all right, at time t. Well, it's going to be equal to e to the minus 2t times the cosine of the square root of 6 times time, and then plus 3 over the square root of 6, e to the minus 2t times the sine of the square root of 6 times time. And there you have it. Where, of course, I'm using the results we derived today in reverse. I need that root 6 upstairs because that's the beta that I made a mistake about earlier today, right? The beta that became blue. The blue beta. There it is. Shall we do another? Let's do another. First thing you got to do is you got to take ownership of the quadratic problem. Once we're bored with the quadratic problem, then we'll go on to other things. But first, let's master the quadratic problem. What's the inverse Laplace transform of, let's say, s plus 7 over s squared minus 4s plus 3? Well, notice that s squared minus 4s plus 7, plus 3 rather, excuse me, plus 3 is equal to what? That's equal to s minus 1 times s minus 3, right? This is reducible. Right? In contrast, the other one was irreducible. When we completed the square, we get a sum of squares. So, customarily, we then say s plus 7 over s squared plus 4s plus 3. Well, that's going to be equal to a over s minus 1 plus b over s minus 3. You have a chance to redeem yourself. If you never understood partial fractions in Calculus 2, well, here's your chance. You can make a right wrong, and partial fractions will welcome you back. Like a long-lost friend. It wants to get to know you. Let's see here, s minus 1. So a times s minus 3, b times s minus 1. In my experience, my friends rarely call me when they move away. I think that's most people, unfortunately. Lose track of folks. Anyway, let's see here. Especially students. Students are so annoying. But, no, just kidding. Mostly kidding. But, this one's easy. You just plug in s equals to 3. That gives me 10 is equal to 2b. You plug in s equals to 1. That gives me 8 is equal to minus 2a. So b is equal to 5. And a is equal to minus 4. So what we're really looking at is the inverse Laplace. So the inverse Laplace transform of s plus 7. I should have given this stupid thing a name. It's a pain to write again. S squared minus 4s plus 3 is the inverse Laplace transform, actually, of minus 4 over s minus 1. And you know what? Let me get to the point here. The inverse Laplace transform is linear, so I can pull that minus 4 out front. You know that? This is really the inverse Laplace transform of 1 over s minus 1, and bring the minus 4 out front. Likewise over here, plus 5 times the inverse Laplace transform of 1 over s minus 3. Sorry about my 5s and s's looking so much alike, but usually context will help you out. Anyway, so that's minus 4. This gives me an e to the t. That gives me an e to the 3t. And there you have it. Questions? Yep.
So this seems like a very similar method to integrals, where we kind of figure out what we want to get so that we end up getting it.
Yes, inverse Laplace transforming is very much like an integration. Yeah. Now, there is a caveat to that. There's something called the convolution theorem, which it sort of is like it would be, well, imagine you had a theorem like the integral of the product was product of the integrals. Yeah, we don't have that theorem for integrals. The closest best thing is the integration by parts, right? There is something called convolution for inverse Laplace transforms, which probably makes them easier than integration in that regard. But it's a slippery business. I mean, let me do something a little bit sneaky here. So here's a non-standard calculation. Non-standard calculation, just for you guys. The inverse Laplace transform of s plus 7. What happens if you complete the square here? S plus 2 quantity squared, right? Oh, excuse me, s minus 2 quantity squared, right? And then what do I have to do? I just added 4. Subtract 1, right? So if you tilt your head and squint, you can see that that's the inverse Laplace transform of s plus 2, right? Over s minus, s minus 2 rather. Over s minus 2 squared minus 1 plus, well, 9 over s minus 2 squared minus 1. Guess what? This is equal to e to the 2t cosh t plus 9 e to the 2t sinh t. With cosh and sinh, it's all the same. And then if you just, collapse these down, what do you got?